Hello everyone, I'm Lulu Yao from USTC. Today I'm going to present our work, Progressive Memory Adjustment with Performance Guarantee in Virtualized Systems. As we all know, cloud computing has been widely adopted in recent years. As a basic technology of cloud computing, virtualization has become very popular. Through virtualization, cloud service providers can offer virtual machines to tenants. In a virtualized environment, memory is very important. On the one hand, the high price of memory makes it a comparatively scarce resource. On the other hand, memory is critical to the performance of VMs. Therefore, it's essential to use memory efficiently in virtualized systems. However, the memory in the current virtualized systems is not being used efficiently. On the one hand, the memory demand of a VM often varies dynamically during the whole execution. In order to cope with the demand peaks to guarantee performance, VMs are usually configured with peak memory demand. On the other hand, when applications running in VMs finish execution, the memory occupied is free, but still can be released to host. A lot of methods have been proposed to efficiently use memory. Dynamic memory adjustment is one of the most representative techniques. In short, dynamic memory adjustment adjusts the memory usage of the host by reclaiming the free memory or inactive memory in some VMs and allocating it to other VMs. It's commonly implemented based on Bloom driver, which provides infinite and deflate operations to support memory adjustment. It's already integrated in mainstream kernels. The common way to use it is to implement a controller in host, which determines the target VM and the amount of memory to be adjusted. When the host needs to reclaim memory from one VM, the controller issues an infinite command to the corresponding Bloom driver. The state-of-the-art Bloom-based method determines the target VM and reclamation size for adjustment, while the adjustment operation is executed by calling the Bloom driver. Since the memory adjusting decisions are made independent each time, we name this method one-shot adjustment. It has two advantages: strong isolation and good compatibility. However, it also has several limitations. The first limitation is that it treats different applications equally. However, these applications may have various memory sensitivity. Reclaiming the same amount of memory for different applications have significantly different performance impacts. So ignoring the memory sensitivity of different VMs may cause excessive reclamation. In our experiments, excessive reclamation results in 41% performance degradation. The second limitation is that it's unaware of memory access patterns. In fact, as shown in the figure on the left, the memory requirements of an application usually change dynamically. However, ignoring the key information may degrade the performance of applications. Memory demand can be met in time without a large difference in performance loss. In our experiments, the difference can reach up to 43%. In short, one-shot adjustment has two problems: unaware of memory access sensitivity and unaware of memory access dynamics. Besides, the VM are usually seen as black box, which means it's hard to know internal memory state and perceive performance impact. To tackle these problems and challenges, we propose PMA, progressive memory adjustment with performance feedback control. For the VM is a black box, we can only capture very limited external information, which can be retrieved easily from the host. PMA uses this information to make a decision. The workflow of PMA can be 3 steps: target VM selection, memory reclamation, and feedback control. Therefore, there are 3 questions to be answered. First, which VM to choose for memory adjustment? Second, how much memory to reclaim each time? Third, how to avoid excessive reclamation. I will present the detailed solution below. Firstly, to select the appropriate target VMs, we need to choose suitable parameters to reflect the memory access patterns accurately. We choose physical memory usage, memory access bandwidth, and page faults as our parameters, mainly because they reflect the amount of allocated physical memory, intensity of reading and writing, the degree of memory lacking. After getting the parameters, we need to evaluate the memory state of VMs in order to select the suitable VMs for adjustment. We design a simple and effective evaluation model that is equation 1, D, S, P. In equation 1 are memory bandwidth, physical memory usage, and page faults, respectively. Ri represents the memory demand of VM. Our basic idea is memory demand of one VM is positively correlated to its memory access bandwidth. Larger Ri means more memory are needed. Vice versa, PMA will select VMs with R below threshold as the target for memory adjustment. For the second question, we propose a progressive memory adjustment strategy. We need to solve two problems. The first problem is how to set the initial reclamation size. We need to consider the difference in memory sensitivity of different applications and set the reclamation size has little impact on the performance. We experimentally obtained an appearance value of 10%, and this value can be tuned by users. The second problem is how to adjust the reclamation size. We double the amount of previous reclamation to accelerate the reclamation process. For the third question, our main idea is to use performance feedback to avoid excessive reclamation. To judge performance degradation, we need to use the change rate of I/O size and page fault to evaluate performance loss. High page fault rate and I/O size surge mean previous reclamations incur memory shortage. We had better stop reclaiming memory from these VMs. To balance VM performance impact, we add an amplification factor in I to avoid continuously reclaiming memory from VMs that have experienced performance degradation. Next, we use experiments to prove the effectiveness of PMA. We ran 20 VMs on our host, and these VMs require a total of 120 gigabytes memory. Each VM has a unique ID and run one application from one benchmark suite. We first limit the size of host memory to 90 gigabytes. That means the memory overcommitment rate is 33%. As we can see, PMA limits the performance loss of all VMs within 10%, which is better than one-third adjustment and no adjusting. To make the performance result more straightforward, we calculate the variance and range of the execution time increment of all 20 VMs. The experimental results show that PMA makes virtual machine performance more balanced. To verify PMA avoids excessive reclamation compared to one-shot adjustment, we further conduct some experiments. In particular, we capture the available memory size of some VMs during memory adjustment. We can see that without feedback control, one-shot adjustment reclaims a large amount of memory and causes a 41% performance degradation. On the contrary, PMA initially reclaims only a small amount of memory, then detects a performance drop and stops reclaiming. As a result, PMA brings only a 4% performance degradation. In these experiments, we just change the number of VMs from 20 to 16. The real results show that PMA still achieves more balanced performance and less performance degradation. In our work, we propose PMA, a progressive memory adjustment with feedback control for full virtualization systems. PMA takes into consideration memory access dynamics and memory sensitivity of different VMs. PMA minimizes the performance degradation of VMs through progressive memory adjustment with performance feedback control. Besides, PMA retains strong isolation between the host and the VMs. More design details and evaluation results are in the paper. That's all. Thanks for your listening.